Okay. So, in the previous lecture we have finished here, that is delta T PSS upon delta Vs is equal to 3.522 angle minus 42.3 degree. This is actually phase lag. So, we have to design a compensator for PA, or what you call, that is why you use PSS, such that this can be completely or eliminated. That means, it will be pure damping. That is why you need a lead compensator. We will see little bit in this course, because it is basically as far as the classroom work is concerned, detail is not possible, right, but we will see how things are. So, if delta T PSS has to be in phase with delta omega r, right, that is your, I mean, if you want to be, it is in phase with delta omega r, that is a purely damping torque, then the delta omega r signal should be processed through a phase lead network, right, so that the signal is advanced by theta is equal to say 42.3 degree, because here theta is equal to 42.3 degree. So, theta is equal to at a frequency of oscillation of whatever we have taken, right. So, that means your, in this case we have considered 10 radian per second, right. So, that is then what we are supposed to do then, the amount of damping introduced depends on the gain of PSS, PSS transfer function at that frequency. Therefore, delta T PSS will be gain of PSS at omega is equal to 10 radian per second into 3.522 delta omega r, right. So, here delta T PSS is equal to delta Vs 3.522 angle minus 42.3 degree, and here the delta T PSS must be equal to gain of PSS at omega is equal to 10 radian per second into 3.522 delta omega r, right. With the phase lead network compensating exactly for the phase lag between delta T and delta Vs, the above compensation is purely damping, right. Therefore, the damping torque coefficient due to PSS at omega is equal to 10 radian per second is equal to that Kd PSS, that is due to PSS is equal to gain of PSS into 3.522. That means this one, that means this one, that means delta VSS, delta Vs, the output of the stabilizer signal, it must be some gain of PSS, and it is processed through a lead network. That means that angle also has to be plus 42.3 degree, such that this thing completely eliminated, the angle should not be there, such that you will get a pure damping coefficient. So, therefore, that gain of PSS at omega is equal to 10 radian per second into that 3.522 delta omega r, right. Now, the damping torque coefficient due to PSS at omega is equal to 10 radian per second is equal to the Kd PSS is equal to gain of PSS into 3.522. If in the previous section that Kd due to AVR action was found to equal to minus 12.27, that is why we have seen just before, right, that Kd is equal to minus 12.27, that we have seen in the previous example, whatever data we considered, right. So, therefore, the net Kd including the effects of AVR and PSS is that minus 12.27 plus the gain of PSS at omega is equal to 10 radian per second into 3.522, right. So, to compensate negative gain, that means this one we can set say Kd is equal to 0, right. If we do so, then you will get gain of PSS at omega is equal to 10 radian per second, right, is equal to 12.27 divided by 3.522. In that case, you will get 3.48, right. This is the minimum gain of PSS required, right, such that this negative damping thing will be completely neutralized. The PSS produces just enough damping to compensate for the negative damping due to AVR action. That means, if PSS gain greater than 3.48, the amount of damping increases, it will be positive. If the gain of PSS now is more than greater than 3.48, then effective Kd gain will increase, right, it will be positive. So, that is the damping increases. If the phase lead network later we will see little bit transfer function of the phase lead network. If the phase lead network provides more compensation than the phase lag between delta Te and delta Vs, that is the output signal of the stabilizer, the PSS introduces, in addition to a damping component of torque, a negative synchronizing torque component also, right. So, this is actually, things are simple, but little bit of understanding is required. So, conversely, with under compensation, a positive synchronizing torque is introduced. Usually, the PSS is required to contribute to the damping of rotor oscillation over a range of frequencies rather than a single frequency, right. Therefore, this one figure number is not mentioned here, this should be I think figure 32, right. So, this figure actually it is figure 32, right. Therefore, just I am cleaning this. So, this is figure 32. So, figure 32 shows the block diagram of the excitation system including the AVR and automatic voltage regulator and PSS. So, this is actually your figure 32, right, and this is power system stabilizer. So, you have input here is delta omega, this is the gain of stabilizer, this is a high pass filter wash out, later little bit we will discuss later, and output of this is delta V2, and this is a phase compensation 1 plus ST1 upon 1 plus ST2, generally phase lead compensator, output is delta Vs, right, and signal is coming here, this delta Vs signal is coming here, and this is your delta V reference, and this is coming from voltage transducer, input to this is delta Et. This we have seen that in the block diagram figure 31 also you can have a look, right, this block diagram everything is there, and this is exciter, gain is K only considered, no transfer function considered here, and output is delta EFD, right. So, actually in that your power system application, this is actually your phase compensation, only one block is taken, T1, T2 you have to optimize, right, it depends on that your what you call that your which system you are applying, and accordingly you have to design the parameter T1, T2 you have to optimize, right. So, here it is only phase compensation, only single block is there, but it may take some other form. For example, sometimes you need multiple blocks, for example, sometimes you need a 1 plus ST1 divided by 1 plus ST2, say another one say 1 plus ST3 by 1 plus ST4, right. So, in this case T1, T2, T3, T4, 4 such parameters are there, but do not confuse this T3 with the previous T3, right. So, do not confuse that with your AVR time constant, right. This T3 means this thing, if necessary I can put T3 dash, right. So, in that case 4 parameters you have to optimize. So, an order of the system also will increase, state variable order will increase. Another form, it depends of course on the system, another form sometimes this is also helpful, 1 plus ST1 upon 1 plus ST2, sometime it is square, right. So, that means 2 parameters T1, T2, but it is square, right. But again in this case that dimension of the system will increase. So, this is actually only one block is shown, right, only one block is shown. So, each block has its your some your what you call some function, later we will see. Since we are concerned with small signal performance, because our objective is the small signal stability, right, stabilizer output limits and exciter output limits are not shown in figure 32, because this is actually I have forgot to wrote, this is actually figure 32 if I recall correctly, because previous figure was 31, right. So, that your stabilizer output limits and exciter output limits are not shown in figure. Stabilizer output limits means here this is also not shown here, no, because it is not required, right. And another thing is that here exciter output limit is also your not shown here, your what you call not shown here, right, because no need, that is why it is not shown, right. So, we will simply go for linear system analysis, right. So, the PSS, that is the power system stabilizer representation in figure 32, right, this is actually figure 32, that previous figure. consists of 3 blocks. One is that phase compensation block, another is a signal washout block, and a gain block, right. So, let me move it up. The phase compensation block actually provides the appropriate phase lead. I told you this is actually appropriate phase lead characteristic to compensate for the phase lag between the exciter input and the generator your electrical torque. We have seen no 3 point something angle minus 42.3 degree. So, you have to compensate the angle, that is why phase lag, that means phase lead characteristic to compensate for the phase lag such that we can get a pure gain, right. So, that is figure 32, it is 32 shows a single first order block. We have considered here first order block, but I told you it may be multiple blocks, sometimes 2 or 3, sometimes square, right. So, it depends on the system, right. In practice, it is written 2 or more first order blocks may be used to achieve the your what you call desired phase compensation, right. So, that means we want pure your what you call pure damping, that means we have to compensate that lagging angle, right. So, in your what you call in some cases second order blocks with complex roots have been used. I mean some cases also second order block also has been used. It depends on the system which will your what you call that damp the rotor frequency oscillation. Normally the frequency range of interest generally 0.1 to 2.0 Hz, right. So, and the phase lead network should provide compensation over this entire frequency range. So, whatever phase lead network you use actually that it frequency for small signal stability, the frequency range is 0.1 to 2 Hz, right. And the phase lead networks must provide the compensation over this entire frequency range. The phase characteristic to be compensated changes with system conditions, right. Therefore, a compromise is made and a characteristic acceptable for different system condition is selected, right. So, this is actually that phase details cannot be done on in the classroom. For that we have to do the simulation work, right. And T1, T2, T3, T4 I mean those lead lag compensator you have to also optimize, right. And for that also it is what you call it is little bit of not easy task, a little bit of complicated task, right. Some optimization technique you have to follow, right. Generally some undercompensation is desirable so that the PSS in addition to significantly increasing the damping torque result in a slight increase of the synchronizing torque, right. Next is that washout blocks, that is STW upon 1 plus STW, that block is here no, that is your washout block, this block, this washout block, right. So, the signal washout blocks actually serve as a high pass filter with the time constant TW high enough to allow signals associated with oscillations in omega r to pass unchanged. Actually, the washout time constant TW I mean a little bit of simulation experience I have, that generally the TW they keep in between 10 to 20 second. If you keep in between 10 to 20 even little less than that also, it does not affect much on the system performance, right. So, it need not optimize, there is no need to optimize, but you can select some value in between 10 to 20 second, right, to allow signals associated with oscillations in omega r to pass unchanged, right. So, it is STW upon 1 plus STW. Without it, steady changes in speed would modify the terminal voltage, right. So, it allows the PSS to respond only to changes in speed, otherwise no, if steady speed is there it will not pass, right. From the viewpoint of the washout function, the value of TW is not your what you call critical and may be in the range of 1 to 20 second. I told you that even 10 to 20 second you keep any value, even below that, below 10 also you will not find any this thing, not much, it will not much affect the dynamic performances. The main consideration is that it will be long enough to pass stabilizing signals at the frequencies of interest unchanged, but not so long that it leads the undesirable generator voltage excursion during system islanding condition, right. So, these are the different feature which cannot be covered in the class, right. but only those things will be covered which are in this which we can do it in as a classroom exercise. Next is, just hold on, next is, right. So, just hold on. Now, system state matrix including your PSS, right. So, same diagram I have redrawn, only one thing I have missed here, that input signal to this is delta omega r. Previous diagram it was there in figure 32, what I said, it was there, right. And this is we are marking as a block 1, this is block 2, this is block 3, this is block 4 and this is block 5. It is marked here 1, then 2, then 3, then 4 and this is block 5, right. And this is your stabilizer gain, this is washout, output is V2 and this output is Vs, right. And this is your V reference and this is exciter and this is EFD, this is the exciter gain, right. So, if we write down the your what you call that because of the stabilizer thing, that this is one state variable has come and this is one more state variable, right. So, in that case what will happen, that we have to write down the state variable equation. So, now this is all these things and this is delta omega r, I told you, right. So, this is actually, this will be then figure 33 or figure 32 actually, right, because it is a repetition same figure, right, but anyway this is figure 33, I did not write it here. So, from this, from the block 4, that means from this block if you write, right, for small part, your small perturbation if you write from this block, right. So, it will become, I am writing here, then I am going this, suppose for small perturbation I am overwriting it, that delta V2 will be is equal to, that you know from your state variable analysis, STW, right, into this input signal is delta omega r, I have missed it here, into K stabilizer gain into delta omega, right. This is your delta V2 is equal to, right. That means I am overwriting it, that look, if you cross multiply, it will be delta V2 plus S delta V2 then TW is equal to K stabilizer then into TW and into your S delta omega, right. Now, this I am writing somewhere here, look from here, it is delta V2 plus this S delta V2 is nothing but your delta V2 dot, right, then multiplied by TW is equal to, this is K stabilizer gain into TW and S delta omega r means it is delta omega r dot, right. Now, if you want to get the state variable equation for this your delta V2 dot for this equation, then delta omega r dot you have to substitute. Now, what you will do, you go back to, if I recall correctly, just check, go back to equation your 267, right, that equation 267, first equation delta omega r dot is given, right, in terms of delta omega r, delta EFD it is given, right. That delta omega r you will substitute here because it is K stab TW into delta omega r, that delta omega r dot you can substitute here such that right hand side dot term will be eliminated, right. So, from equation 267, in this equation you put delta omega dot is equal to, all these things I have not written, then it will take long time, right. So, just you can put it and you will get it, right. So, that is why this equation we are writing S delta V2 is equal to K stab S after simplification delta omega r minus 1 upon TW delta V2. That means, this S delta V2 is nothing but delta V2 dot, because we know that S represents d dt and all initial conditions are 0, say, right. So, is equal to K stabilizer gain, right, S delta omega r means it is delta omega r dot minus 1 upon TW delta V2, right. So, delta V 2 is another state variable. So, this delta omega dot equation you substitute here that delta omega dot expression here, right. So, at the right hand side this derivative term will be removed from equation 267, the very first equation that you substitute here, right. If you do so, then it is actually same thing 267, here it is 285, right. I think if you look into that S delta omega is nothing but delta omega dot either 267 or 285. I think from equation 285 I have substituted here, right. So, just check, right. So, then we obtain the following expression of S delta V 2. You check equation 267 or this here it is written 285, right. So, just you put delta omega dot equation and that is all, right. So, if you do so, then this equation S delta V dot delta V 2 is equal to K stabilizer A11 delta omega plus A12 delta delta plus A13 delta psi f d plus 1 upon 2 h delta T m minus 1 upon T w delta V t, right. So, basically S delta V 2 is nothing but your delta V 2 dot. So, delta V 2 dot is equal to K stabilizer into all these things, right. Equation number I think I have written later, right. So, that means this S delta V 2 I have kept it as S delta V 2, this is nothing but delta V 2 dot. So, delta V 2 dot is equal to basically it is a fifth equation because equation 285 is a fourth order, that equation 285 it is actually 4 into 4, that A matrix, it is a fourth order, right. Now, because of this thing the order will increase. So, that is why we have this is a your what you call this delta V 2, it is actually your fifth state variable. So, it is A5 delta omega we are writing plus A5 to delta delta plus A53 delta psi f d plus A55 delta V 2 plus K stabilizer upon 2 h into delta T m. This is equation 296, right. So, this is simple thing, just you will put it like this, where A51 is equal to K stabilizer, that is stabilizer gain into A11, A52 is equal to K stabilizer into A12, A53 is equal to K stabilizer A13 and A55 is equal to minus 1 by T w. This is equation 297. Since S V 2 is not a function of delta V 1 and delta V 3, that is this S V 2 means it is delta V 2, S delta V 2, right. It is actually delta V 2 dot. It is not a function of delta V 1 and delta V 3. So, A54 and A56 basically 0, because right hand side delta V 1 and delta V 3 are not there. So, right hand side of this equation this is not there, right. Delta V 1 and delta V 3 is not there on the right hand side. That is why that your what you call that your A54 and A56 is equal to 0, and this is actually S delta V 2, that is your delta V 2 dot, right. So, this is fifth equation. Now, next is that phase compensation block, that is block 5. Now, in the block 5 also you can write for small perturbation delta V s is equal to delta V 2 into 1 plus S T 1 upon 1 plus S T 2, right. Or if you simplify this equation, then your S delta V s will be nothing but delta V s dot, right. Similarly, S delta V 2 will nothing but delta V 2 dot, right, plus 1 upon T 2 delta V 2 minus 1 upon T 2 delta V s, right. So, from equation 296 you substitute here delta V 2 dot, because this is delta V 2 dot, right. Therefore, from equation 296 here it is, that is your here it is, right. This equation 296 you substitute here, if you do so you will get that S delta V s, that is your nothing but your delta V s dot, right. is equal to A61 delta omega r plus A62 delta delta plus A63 delta psi f d plus A64 delta V 1 plus A65 delta V 2 plus A66 delta V s plus T 1 upon T 2 into K stabilizer upon 2 H, right, that stabilizer gain upon 2 H into delta T m. This is equation 298. So, this is the sixth state variable. So, when that your different component you are considering, then what is happening, that your order of the system is getting increased, right. So, where A61 is equal to T 1 upon T 2 into A 51, A62 is equal to T 1 upon T 2 into A 52, A63 is equal to T 1 upon T 2 into A 53, A65 is equal to T 1 upon T 2 A 55 plus 1 upon T 2, right. Similarly, for block 2 of above figure, I mean if you go to that block 2 of this figure, right, here it is, I am going and just earlier also we have discussed from here, if you write small perturbation equation, right. So, it will be your what you call the delta EFD is equal to delta V reference, right, minus your delta ET into 1 plus STR, right, from this block, I mean from here only, from here only, including this one, right, small perturbation one, we take only delta ET, delta EFD. If you do so, just open the block diagram, you yourself can easily do it, right. So, from block 2 of above we can write delta EFD is equal to K into delta Vs minus delta V1, right. So, that means this one, actually this one previous figure it was there, this is actually delta V1 and this is delta Vs, which is here small perturbation Vs, small perturbation delta Vs, it was V1 small perturbation delta V1. So, this is actually delta V1, in this figure I have missed it, but previous figure it was there V1, right. So, this is delta V1. So, your basically your if you write in small perturbation, this is also delta EFD, right. So, in that case delta EFD is equal to your Ka, right, that exciter gain into your what you call delta Vs, right, plus delta V reference minus delta V1, right. But if you say delta V reference is equal to 0, then it will be simply delta Vs minus delta V1. So, here it is, right. So, delta V reference we have considered that thing is 0. So, delta V reference in that case we have considered it as 0, we have considered only delta Tm, right. So, this is delta EFD is equal to this equation, right. So, now the field circuit equation with PSS includes, it become that your S delta psi FD is equal to A32 delta delta plus A33 delta psi FD plus A34 delta V1 plus A36 delta Vs, right. And this one again you please go back to the state variable equation, right, and then S delta psi FD means it is delta psi FD dot, right, is equal to this expression, this is equation 300, right, and A36 is equal to omega 0 RFD upon LADU into K. Just you have to modify those equations because delta EFD is equal to this much, right. And therefore, the complete state space model including your PSS has the following form with delta Tm is equal to 0. If delta Tm is not there and delta V reference also we have set 0, say for example. So, this is the order, but anyway for the analysis you have to consider the step input for delta Tm, that is why delta Tm second term I have not written. So, this is your equation 302. So, thank you very much, we will be back again.